Hello, everyone. Welcome to the webinar on anomaly detection using machine learning. This is the fourth session out of a total of 8 sessions in this webinar series. So today's topic is anomaly detection for multivariate data. So that means the data has multiple dimensions, and the different dimensions are, there's significant correlation between the different dimensions, or you can say the significant cross correlation, but not much autocorrelation or temporal correlation. Or the data may not be sequential at all. That means the order of the data doesn't matter. So only thing that's significant is the correlation between the different dimensions. So going back to that one example you looked at in an earlier session of the response time for a service ticket in a ticketing system, although each ticket has a timestamp, it really is irrelevant. So just because there's timestamp with the data doesn't mean that it's a time series or it's autoregressive. So those are the kind of data that we are focused on today. And so there are a set of algorithms that apply for when you have this kind of data. We'll be going through a very quick overview of some of those algorithms. So this list is by no means exhaustive, but these are some of the algorithms that are more popular and well known. So the first one is it's kind of no-brainer. It's very intuitive. So what you do is your data is multidimensional. So what you do is you use nearest neighbor algorithm. So it's like the KNN algorithm in machine learning, except that we are using it for anomaly detection, not prediction. So you calculate the distance between any data point and its k nearest neighbor. And after that, you can calculate the anomaly score in two ways. You can either hold on. Yeah, so you can either take the average distance to the k nearest neighbor, or you can specify a distance threshold and count the number of neighbors within the distance. So there are two options, and each one will give you an anomaly score. So obviously, for example, if you take the average distance to k nearest neighbor, higher the distance, more anomalous the data is. That means the particular point that we are considering, it lies in a low density region in the feature space. So this one is computationally intensive. It's model free. It doesn't build any model with normal data, but it's computationally intensive. So the next one is called local outlier factor. It's also based on neighborhood-based algorithm. It looks at density of a point in the neighborhood. It also takes into account the density of all the neighbors for a given point. So it's a little bit more complicated than nearest neighbor, but the claim is that it's better than the plain vanilla nearest neighbor. It'll calculate something called local reachability distance and local reachability density. So I'm not going to the all the technical details of this. You can search, and you will, if you do a Google search, you'll find lots of information on this. So you can read up all the technical details. So the anomaly score is the average ratio of local reachability density of neighbor and the point under consideration. This one is also computationally intensive, actually more than the first one, because there's a lot of additional computation it has to perform. This one is also model free because it works straight on the data without building any model. Isolation forest is another interesting one. here the intuition is that if you so just like random forest, you build a bunch of trees. The big difference is for each. So you build the tree iteratively in when you build a decision tree. So you select some attribute and then you find a split point in that attribute, some value of that attribute, and then you partition the data around that point. In case of decision tree, that splitting logic is based on information theory like entropy or Gini index. But in this case, you just select it randomly because the purpose of this is anomaly detection. So you keep doing that and you grow each tree until each leaf has only one node, or until the tree reaches some maximum depth, which is pre-specified. Now, if you think of it intuitively, if a point lies in a low density region in your data space, then your length of a path to a point, in a tree will be longer. So longer the path to a given point in a tree, more likely it is to be anomaly. So you can use an expression based on that path to define your anomaly score. So what is done is that you calculate the path for any given point. Let's say you have used 100 trees. You calculate the path of a given point in each tree, and then you take an average of all that. So if it's a sparsely populated region in the data space, then it'll have, I'm sorry, what I said about the path is for normal points. I'm sorry about that. For data that's in a low density region of the data space, the path will be smaller, which makes sense, because if the path is in a dense region, then you'll keep on splitting until you get to that point. So your path will be longer. So you'll have you'll have a longer path through the tree if the point lies in a dense region. And exactly the opposite is true for points in the sparse region. And any point in the sparse region is likely to be an outlier. So I'm not sure if you want, if that should be called a model. It's not, although you're building a tree, but you're not really building a model. So it still is, model free. Clustering, the intuition is that after you build a cluster, there are some metrics which defines the cluster membership of any given point. Okay, so weaker the cluster membership of a given point, more likely it is to be anomaly. So that's the intuition. And there are different ways to define cluster membership. So, for example, it could be as simple as the distance of a given point to the centroid of the cluster, right? Compare, and it could be that that distance and divided by the average distances of all the points to the centroid. I'm just saying, that's an example. There are various definitions of cluster membership metrics. So poorer the cluster membership, more likely it is that the data point is anomaly. So you can tie your anomaly score to the cluster membership value. There is some extension to the basic clustering algorithm. So for example, there's an algorithm called CBLOF. So in this algorithm, it maintains two sets of clusters, large clusters and small clusters. And there are some criteria which defines, what's a small cluster and what's a large cluster. And then it defines cluster membership, and the definition is different depending upon whether a data point belongs to a small cluster or a large cluster. There is another extension to that called LDCOF. It's an extension of CBLOF, but it takes into account the density of a cluster. So it's a little bit more advanced than C block. So the next algorithm is dimension reduction. So you can take your multivariate data and you can do something like kind of feature engineering you might do to reduce the dimension. For example, you might use PCA, or you might use autoencoder, as in deep learning. The big difference between the two is that the PCA will do a linear transformation to a lower dimensional space, whereas with autoencoder, it can be nonlinear. For example, if you have hidden layers and activation functions and all that, you'll get a nonlinear lower dimensional space conversion of your data. So for example, if you use autoencoder, the output of the encoder is your reduced dimensional space representation of the data. And once you have done that, since in the reduced dimensional space, the data, the different dimensions are decoupled from each other. One thing you can do is you can take each of those dimensions and treat each of them as a univariate anomaly detection problem. The data originally had let's say 15 variables, and with autoencoder, let's say you compressed it down to 5 variables, from 15 to 5, which is called bottleneck in autoencoder. So what you can do is you can take each of those and just apply any univariate anomaly detection algorithm. So with any of those variable, if you find an anomaly, that data point is basically an anomalous data point. So let's say you found that you had 1,000 records, and you found that, and you had a dimension of 15 to start with, you brought it down to 5, and then you're looking at, let's say, the first dimension, and you found that the fifth data point is anomalous. So what that means is that the fifth record in your data set in the original dimensional space is an anomalous record. So you can repeat that for all the different 5 dimensions, and you can detect anomaly that way. So that's one way of using autoencoder. The other way, which is more common, is you train an autoencoder with normal data, and then for prediction, you process your test data through the autoencoder. Then what you do is you find your regeneration error, which is the difference between the decoder output and the original data. So higher the regeneration error, more likely it is that the data point is anomaly. Because if it's a normal data point, the regeneration error will be very small. Because the whole point of anomaly, autoencoder is to, for a given data of some given dimension, it finds all the hidden patterns. So the encoder output is essentially a representation of the same data in a lower dimensional space. So for normal data, the regeneration error will be very small, but if it's anomalous, the regeneration error will be large. So that way you'll know that you have an anomalous data point, and your score could be defined in terms of that. The outlier score. It could be defined in terms of that regeneration error. And for autoencoder, you can use any deep learning library, for example, TensorFlow or PyTorch. And also there is a Python anomaly detection library called PYAD. So they also provide an API for anomaly detection using autoencoder, but under the hood, they just use TensorFlow. But it just makes it a little bit easier to use for anomaly detection. instead of using TensorFlow directly. One other kind of algorithm that I didn't mention here, it's kind of a special category, is for, excuse me, when it comes to finding anomaly in image, there are a lot of application in the medical domain. So for example, you may have some X-ray image and you want to find out if there's anything abnormal. So people sometimes they'll use a CNN convolution neural network, and they will use classification. But sometimes the preference may be, instead of using classification, is to just frame it as an anomaly detection problem. So you take your normal images, build your anomaly detection model. Anything that is anomalous is essentially, it means that there's something wrong. There's something wrong with the patient. It's not normal. And for anomaly in images, there are two approaches. One is, there are various approaches, but the two most popular ones are, and they both use convolution network. So one is based on autoencoder. So you basically have a convolution autoencoder. Again, here the solution is very similar to what I just mentioned about autoencoder. You take the difference between your encoder output, the decoder output and the original image. And if that error is large, there is something anomalous in that image. The other solution is more complex. So there is something called, in deep learning, there's something called Gan Network. It's generative adversarial network. So what they do is, this network has two parts essentially. There is a discriminator part, which is like a basic classifier for image that could be based on CNN. And then there is something called a generation part. So what that does is that, so it's like a game. So the discriminator will essentially classify, and it'll classify whether something is real or fake. So it's like a binary classifier. So the generator will try to fake an image, and then if the generator has been able to fool the discriminator, that means the generator is working really well. It's being able to create realistic images. So this GAN network can be used for anomaly detection also, by looking at, so there are two kinds of error here. There is a discrimination error, and then there is the generation error. So combining these two, you can define define an anomaly score. So the GAN also can be used for anomaly detection for images. So that's kind of a special topic, and it's kind of bleeding edge, and there's a lot of papers, and there's a lot of research going on in that area. But most of the application seems to be in medical area, but there are a lot of other applications also. For example, in in engineering, for example, defect detection, and a few other use cases are there. So let's see. So these are the algorithms. So what I'm going to do for use case, I have two use cases. One is based on the data set that we had looked at earlier. It's for a service ticketing system. So it's very simple data set. It's got 3 fields. Let me show you. It's got for each ticket, there is a ticket ID, and there are few fields that are not relevant for us. There is service center ID, and then there is a timestamp, and then the 3 important fields are the priority of a ticket, the severity of the ticket, that means how complex the issue is, and the time it took to resolve. So our goal is to kind of monitor the performance of the ticketing system to by looking for any anomaly in the service time. So for example, if it's a ticket with low severity, which shouldn't take much time, and it's taking it took a unexpectedly long time, that's anomalous, and we want to detect that. So essentially, it's for monitoring the performance of a service center. So for this, we'll use this isolation forest algorithm. So isolation forest you can get from either scikit-learn or this other library that I talked about, PYAD. But I have a feeling underneath they use scikit-learn. I haven't tested it, so but that's my guess. So here, so this is the data, and what I have done is I have a plot here. So this is a plot for the first 20 records in my data set. Here we don't see any anomaly in the first 20 records. Any anomaly is basically this red vertical line. All these other 3 lines, they correspond to the 3 dimensions of the data. Like I mentioned, the priority and the severity and the resolution time. This red one is the resolution time. In the next window, the next set of 20 records, we find a few anomalous records. So I think once we had done what we had done past with this data set is that we took this data set and we kind of treated this as a single dimensional data set. So we just looked at the service time and applied a univariate anomaly detection algorithm to see anything anomalous, to see if there is anything anomalous or not. But it completely disregarded the other 2 variables, the priority and the severity. So for example, like I said, if the severity is low, you expect the service time also to be low. And if that's not the case, then it's anomalous. But what is anomalous depends on the other dimensions also, right? So for example, or if it's low severity and it takes, instead of taking 1 day, it takes 3 days, that's anomalous. Whereas for high severity, 3 days might be normal. So that's how the the cross coupling between the different dimensions come into the picture when you do multivariate anomaly detection. And that is the reason you cannot take each variable as a univariate data stream and apply univariate anomaly detection algorithm, because a naive solution for any anomaly detection is to take each dimension as an independent variable and apply univariate anomaly detection algorithms and then kind of combine them all together. But that's not going to work because it completely disregards the coupling between the different dimensions. Excuse me 1 second. So that's the first use case. So there's one parameter in isolation forest algorithm in scikit is that what they call impurity. So you have to tell the API, what fraction of the data you think is anomalous, and based on that, it'll it'll tell you whether a given record is anomalous or not. So it doesn't actually give you the anomaly score. It just returns say 1 or -1 for each data record. 1 means it's anomalous, and I forget which. No, I think -1 is anomalous. And so this impurity is kind of like, I think last session or the one before, we talked about this issue of outlier score threshold, which is, so the issue is, how do you know what threshold to use? I mean, it may seem to be kind of subjective. You can just set it to some, you can just pull out of thin air and you can say, okay, that's my threshold. But there has to be some justification for that. So one way of doing that was, as I suggested, is I actually showed some results also, is to take all your outlier scores and do statistical tests. And you might say that anything within 95% confidence is normal. So outside that, it's anomalous. So I think this impurity is something similar, although they call it impurity in scikit-learn. You are essentially specify your confidence bound for normal data, or in this case, 1 minus your confidence bound. So I use 0.1 as if I'm expecting 10% of the data to be outlier. So it's something you set, and according to that, it will label in the result. It will label your data as either outlier or normal. So the next use case is it's kind of interesting. It's got a lot more dimensions. So the data is, there are 7 dimensions, the 7 fields in this data set. So here the problem is, there are some, I was reading some reports about what kind of visitors a website has, for example, some e-commerce website or something like that. And they think that half of the visitors are essentially bots coming to a website for various things. So I mean, we know about the search engine bots, for indexing pages. So they are always there, but there are a lot of other bots who might come in and steal content from your site. They might be scraping and looking for information, and they might just steal it. So the problem is, how do you identify those bot sessions? So you may have session data from your web server, and you want to identify those bots, and then maybe you want to take some action, based on that. So in my data set, the 7 variables or the 7 dimensions are in any. So there's 1 record for each session. So, and the session has some finite duration. So the variables are number of pages visited, average time spent per page, fraction of pages visited, that are, for example, product review related. So if it's a e-commerce site. So if in a session, if most of the time is being spent on the product review page, it's kind of suspicious, right? Because they might be trying to gather some information about your product, maybe price or some other information. Then whether in that session, whether items were put on in a shopping cart, that's a binary. So the next set of variables are all binary, and the next one is whether whether there was any completed checkout in that session. And then the last one is whether there was an explicit logout from that session. So there are 7 variables involved. And in this case, although there is a timestamp associated with each session, we are not considering it as a time series or any kind of, having any kind of temporal correlation. If we did, then it will belong to another category of data set and different kinds of algorithms. So in that case, it will be multivariate autoregressive data, or multivariate data with temporal correlation. But in this case, our assumption is that there is no temporal correlation. It's only the correlation between the different dimensions. So we have 7 dimensions here. And you can find out, whether how much correlation you have by doing, pairwise, cross correlation. You can calculate like Pearson correlation coefficient, which we did in the very first session, which was dedicated for data exploration. So you can use some of those techniques from that session if you're interested to find out what kind of correlation you have between the different dimensions. So we are not going to do that for this data set right now. We'll just jump straight into anomaly detection. So for this, we'll be using autoencoder, and our anomaly score will be based on the regeneration error. So for autoencoder, I mean, you could always use TensorFlow or PyTorch, but for this demo, I'm just using this PyAD library, which uses TensorFlow under the hood. So I have 2 data sets here. One data set is normal, so as if the data has been curated somehow and all the outliers removed, and then we use that normal data set to train a autoencoder model, and then once we have the model, then we run the real data through that autoencoder, and then we look at the regeneration error, and depending upon the error, we flag a data record as either anomalous or not. By the way, in all the algorithms that we have looked at so far and that we'll be looking at in future, they are either unsupervised or semi-supervised. So unsupervised is, for example, that nearest neighbor algorithm. Okay, that's unsupervised. And by semi-supervised, I mean that you build a model with normal data. So we haven't covered any supervised algorithm, like when you have labels for normal data and anomalous data, and you set it up as a classification problem. Generally, that's not done for anomaly detection because most of the time you're dealing with highly unbalanced data, and that's not very generally, it's not solved as a classification problem. And the other issue is that it's difficult to label what data is anomalous. So because of all these difficulties, the full-blown supervised model is never built. It's either unsupervised or semi-supervised. So again, for semi-supervised, you take normal data and you build a model. The semi-supervised is kind of like in one class classification. So here, so I'm using the PyAD library, and this is all the output that comes as the autoencoder model is being trained. This is coming straight out of TensorFlow, I think. The different mini batches, epochs and batches and all that. And then it shows also the loss. Here, I started looking at the output. Here, the blue line is the anomaly score, and this red vertical line is anomaly. I set the threshold kind of, I just set some threshold. I haven't really done any statistical analysis, but that's what should have been done, but I haven't done that. I just set it to, I think, 17 or something in this case. This is the next set of 20 records. Again, each record has 7 dimensions. So this one has 3 anomaly records, as we can see. One other thing I wanted to show you is the network, the autoencoder network architecture. So in the code, you specify it here. Oh no, that's actually, that's the, sorry, that's the wrong one. See this array 7, 5, 3, 5, 7. So let's understand what that is. So so each number is the number of units in a given layer. Okay. So in this case, this is the input layer, which is 7 because our dimension is 7 for the data set. Next, we have a hidden layer with 5 units. Next, we have the encoder output, which is 3 units. Okay, and then this network is symmetrical. So autoencoder looks like a butterfly essentially. So this is the encoder output, and then this is another hidden layer on the decoding side. And then again, the output is 7 because output has to be, same as the input, same dimension. Not only the dimension, but also the output value should be very close to the input values when the network has been trained properly. So this is something I chose. Obviously, in reality, we'll be doing experiments and looking at errors and try to choose an optimum architecture. But the first and the last number is dictated by the dimensions, number of dimensions you have in your data set. But anything in between, it's up in the air. I mean, you can choose your whatever architecture works best for you. So that's the. So this is why this PyAD library is useful, because it provides a user-friendly abstraction on TensorFlow, which is designed for anomaly detection only, because autoencoder has various other usages besides anomaly detection. But this library only cares about anomaly detection, so it's been nicely abstracted for anomaly detection. So let's see. One second, I'm running low on my battery. Let me plug in my power. Let's take a quick look at the different algorithms as far as the implementation goes. So you'll find some of these in that PyAD library, some of these algorithms. Nearest neighbor, you can just use the machine learning library, like I think scikit also has some. Local outlier factor is local. I use plus any clustering implementation. Dimension reduction, if you're using autoencoder, you can use PyTorch or TensorFlow. This one again, PyTorch, TensorFlow, or PyAD. And for that image anomaly detection I talked about, that's a little bit more complicated. So you have to use deep learning libraries directly, either PyTorch or TensorFlow. You have to set up your network as a autoencoder or GAN using CNN as the building block. So I think that's it for this session, and I'm open to questions.
Pranab, if you can see from the Q&A window, there are a few questions already there.
Okay.
So Yeah, do you want me to read through it or?
Let me see if is there
Yes,
any way I
it's in the
can
Q&A.
let me see if I can get to that directly. Let me try that. Yeah, you know, it's I think I attend the Zoom through whenever I attend the Zoom through web, I don't see everything in the menu for some reason instead of the Zoom app.
Never mind, I'll just quickly read the questions. First question was, does finding a coordinate axis in multi-dimension data to be clustering and dimension reduction?
Sorry, say that again.
Okay, I'm just reading as is. Does finding a coordinate axis in I think he intended multi-dimension data to be clustering.
I'm sorry, the first part is what? Coordinate axis.
Yeah, coordinate axis.
I'm not sure what that means.
Yeah,
anyway,
the question, question is not very clear though. Also, there's another one. Do you equate principal component analysis with clustering? Do you equate principal component?
Let's see. Not really. They are two different things. I mean, the principal component is all about taking your data and reducing it to a different dimensional space. Whereas in clustering, you're staying in the original dimensional space and you're doing clusters. Although, I mean, you could apply clustering after dimensional reduction also. But other than that, you know, they're separate. Anything else?
Yes, the next one is, can you explain the non-linear nature of autoencoder? Is it just unspectable nature in the DNN, or is there a non-linear partial differential nature or other functions that can be inspected?
Okay. No, it's simply nonlinear for the same reason that deep networks are nonlinear. You know, you have hidden layer and then you have nonlinear activation function. There is nothing special in the autoencoder that makes it nonlinear other than what makes any deep network, you know, nonlinear with hidden layer and activation functions. And it's fundamentally different from PCA because the PCA, the dimension reduction is a linear transformation, whereas in autoencoder it's nonlinear.
Shall I take the next one?
Yeah, sure.
Yeah, with the GAN, there's an interesting concept called the Z space, which allows the implementation of something like a PCA axis in the generated image or matrix. Is that related to dimensional reduction in previous methods discussed?
Well, I mean, if you look at any deep network, there is always dimension reduction because deep learning is mostly about feature engineering, you know, dimension reduction, however you want to put it, finding hidden patterns in a hidden vector. So any deep network, there is always, you know, dimension reduction and hidden pattern recognition going on, always. Any non-trivial, you know, deep learning network. So that's always the case. So for example, when you look at the discriminator part of the network, so the discriminator underneath, for example, for an image, it may have a CNN, which is doing essentially feature engineering and dimension reduction, right? And only the last layer that does the classification. Everything else is pretty much feature engineering and dimension reduction, and all complex nonlinear. And same thing on the generator side also. You know, you take some data from some distribution and then you try to learn the actual distribution of the data. So there is also, you know, feature engineering going on there. although you're going in the opposite direction.
Done answering,
Next.
Pranav? Yeah. Also, meanwhile, participants, if you want to ask questions directly, you can indicate by raising your hand. We will unmute you. Okay. There's another one there. How to download and practice this Jupyter notebook?
This Jupyter notebook is in my GitHub repo. So one of the earlier session has a link to the Jupyter notebook. In this session, I didn't provide the same links, but one of the earlier sessions, either the last one or the one before, in the Google Doc, there is a link to the Jupyter notebook in my GitHub repo.
Yes, we have shared the Google Doc with you. So hopefully you'll be able to find it there.
Yeah, there should be a link in one of the sessions.
Anybody, if you want to ask questions, you can raise hands. We will unmute you. Make use of this time. Or even you can put your questions in the Q&A box, whichever is convenient for you. Pranav, do you want to talk about what's the next session going to be? Session 5, which will happen on the
briefly. So the next one is so in the first session we talked about 4 different categories of data, depending upon whether the data has spatial correlation, temporal correlation, or both. So today was a 3rd category, which has only spatial correlation, that means correlation between the dimensions, but no temporal correlation. So the next one is the most complex type, where there are correlation going on temporally as well as spatially. And most of the solutions for this kind of data is almost all of them are deep learning based. Either some variation of autoencoder or GAN. I mean, that seems to be the the most common approaches. So in the next one, it's more kind of R&D oriented. So we won't necessarily have a actual demo and all that, because it's mostly R&D. So we'll talk about some of these solution approaches. Almost all of them based on deep learning. And so that will be the the topic for the next session. It's kind of bleeding edge. So we'll talk about some solutions, some research that's being done, but no actual implementation, because that's a lot of work, and that's not easy to just set up for a quick demo. You have to have a complex, deep learning model and all that, which is going to require a lot of resource. So it'll be more on solutions and ideas and research directions for the next one.
Pranav, there are 3 more questions here. The first one is, I'd like to hear more about understanding the non-linear nature of higher dimensional data.
Non-linear nature of higher dimensional data.
Yeah.
So that's kind of a very generic question. So without some context, it's hard to respond. So non-linearity where? In data transformation, or yeah, I'm not sure. I mean, the data itself could be obviously non-linear. So
if you could make your question more clear with
yeah,
respect
I need
to
some
context,
context on that.
Yeah.
Yeah.
Okay, there's one more there. There are some graphical techniques that map cycles or create projections.
There are some graphical methods to
I
map
don't know if the
cycles.
question was, are there some graphical techniques that map cycles or create projections?
Again, it's a little vague. I mean, cycle of what? The like cycles in the data? I'm not sure what's the cycle intended to mean here.
Yeah, probably I can just unmute the participant there. It's, I think it's Mike. Mike, do you want to ask your questions here? I think there seems to be no answer there.
Okay.
Never mind. Okay. Same question. I think all these questions are related. It's from Mr. Mike there. Did any of the methods discussed today include analysis of the modeled system? Hidden model may not be acceptable in many situations, as one cannot say why they make the decisions that they do.
I mean, on how to select what model to use?
Yeah, include analysis of the model system.
Yeah, so these are all different approaches. So it's very hard to come up with some simple rules as far as, you know, what algorithm and what model will be appropriate for you. You know, it's going to require, you know, a lot of trial and error and experiments for the data set that you have before you can decide. So only thing I can say is that use the simplest solution that works. I mean, that's you know, that's one rule I follow in general. So beyond that, it's really hard to say, you know, unless you have done a lot of exploration and, you know, did some experiments, try different algorithms, it's literally impossible to, you know, make any recommendation.
All right, yes, there were some interesting questions there. You can also continue asking questions. You can drop us your questions at the email mentioned in the chat box. It's info@elephantscale.com. Yes? Anything else you want to add in conclusion, Pranav?
No, thank you everyone for attending. So we have 4 more sessions.
Yes.
So I hope to see everyone in the remaining sessions also.
Yes. Yeah. Thank you all so much. And we will be sharing the recording of this session as well as the class notes shortly. And the next session will be on December 4th, session number 5. Yeah. Yes, we will share the recording as well as the class notes shortly. So
okay.
Thank you all so much. Everyone. Thank you, Pranav. Thank you very much for your valuable session. Thank you.
Sure. Yeah. Thanks, everyone. Bye-bye.